Hello ladies and gentlemen, and welcome back to GGS 300. This week it's going to be the 7th lecture and we're going to be focusing on estimation and sampling. Congratulations on completing the midterm exams and taking advantage of those pre-exam ungraded tests that I set you. It looks like we had some great marks on there, so very well done to all of you. This week I'm going to be setting the 5th assignment, which is going to be due on October the 14th, okay? So that's basically going to be picking up on a lot of those things that we covered today, both in this kind of more abstract lecture where I'll go over the basic concepts, and then also picking up on the kind of R work that we're going to be carrying out in the practical session directly after this lecture. So please don't hesitate to reach out to me if you've got any queries about any of this, if you've got any questions that you would like clarification on. I'm excited to be on campus now, so I hope I'll be able to catch up with some of you, maybe even in person. So don't hesitate to reach out to me. So today we're going to be focusing on estimation in data sampling, okay? And we're going to be focusing on a variety of different concepts. We're going to be focusing on something called the central limit theorem, and then we're going to be looking at things like confidence intervals and estimating sample sizes, okay? So this is the content that we're going to be covering today. Make sure that you cover the associated book chapter, and that's listed within the syllabus, and make sure that you read that in combination with covering the things that we're going to be looking at here. So what do we use samples for? And hopefully you've kind of already got a feeling for this because we've covered it in previous sessions. So we've focused on it when we were on the descriptive statistics part of the course. We've also briefly touched on it within the probability lecture, and also last week when I covered the actual sampling approaches lecture as well. Okay, so please don't forget that there was also that lecture last week that needs to be covered, which could be tested on. And that's basically going to set you up for what we do today, which is basically think a little bit about how we generate these samples. Okay, so what do we use them for? Well, we basically use them as a kind of efficiency tool for actually trying to understand populations that maybe we don't want to carry out a full census on because that's expensive to do, it's time consuming, etc. And then we're able to use that information to actually essentially estimate the population parameters, okay? So whether that's the mean value, or look at the variance in a distribution, or think about the standard deviation, which could be present in an overall population, okay? So we use point estimation to approximate certain values for a population, but then we also use interval estimation, and we haven't really covered this yet, but we're going to touch on it today. And that's basically where, rather than saying we think that the value of a population is X based on the sample that we have, it's where we say that we think a value for the population lies between a range of X minus 3 and X plus 3. Okay, so that just gives you a little bit of an example of what we're going to be covering today. So point estimation, well, that's fairly easy. So imagine that we wanted to estimate the mean of a population. So let's just use my kind of quintessential example. Let's say that we want to look at house prices in the city of Fairfax. Essentially, we could approach this by taking the sample mean. Okay, so that's one of the easiest ways. So X bar equals the sum of all xi values in the sample. So obviously this is a sample, we've got lowercase n, divided by the total number of observations in that sample, okay, and that will give that x bar value. We can also do this for the population standard deviation. Again, the best way to estimate the population standard deviation if you've got incomplete data is basically to take the sample standard deviation, okay, so we want to obtain this value s, and the way to do that is to take the square root of the sum of the squared deviations as the numerator divided by the number of degrees of freedom, okay, and that will produce this this sample standard deviation, which is the best way to represent the overall population if you don't actually have all of that desired data. Obviously, in the standard deviation example there, we're actually using n-1, the number of degrees of freedom, and I've covered this before in a little R example, basically, where I demonstrated that the reason why we do this is because when we sample, we've got a smaller sample. It probably means that we don't have all of the extremes in the actual sample that we've got that is present in the population, and then as a consequence, this prevents us from getting kind of skewed results as a result. Okay, So the smaller denominator helps to account for those missing extreme values. And it's really important if you've got really small sample sizes that you take this into account, okay? Interval estimation. So that was the point estimation that, to be honest, we've kind of already covered in the previous lectures, so that shouldn't all be new information to you. The difference now is that we're going to think a little bit about actually estimating an interval for where we think a parameter lies, which is probably much more realistic to what we would probably do if we were going to write an academic paper, for example, do something more rigorous than just making a single point estimate. So the question is, how close do we think our sample statistics are when we pulled them from the population to the actual true population parameters, all right? So we need to estimate the point statistic to a defined degree of confidence. So the confidence interval is basically defined as this equation here. So essentially for a certain confidence interval, let's just say we want to be 90% confident that our population mean lies within this range that we're going to give. Then the population statistic is expected to be within the interval of x bar, which is the sample mean, plus or minus this tolerable sampling error value that we're going to estimate, okay? So that's essentially how we do it. This is obviously very kind of abstract and quite high level, and therefore I'm going to give you quite a few examples in this lecture today using real numbers, and then we'll kind of cover it in the actual R session for you to get your head around it. And then hopefully by the time you've also read it in the book and done the assignment, this will be kind of fairly concrete in your understanding. Okay, so before we begin, there's an important theorem that I need to just raise with you called the central limit theorem. Some of you may already have heard of this before. If you haven't, then don't worry about it. We're going to cover it here, but it's one of the most important concepts within statistical inference, okay? So essentially, let's have a hypothetical example. Let's draw a random sample of size n to compute a desired sample statistic. Let's just say the mean, and we're going to draw it from a population of properties in Fairfax City, and we're going to look at the house price each time. Now, if we repeat this sampling process many times, then each sample statistic has a distribution, okay? So that's whether we're choosing the mean or the standard deviation, etc. But let's assume here that we're just going to focus purely on trying to obtain that mean house price value, okay? So essentially what we're doing is we have a population with a mean mu and a standard deviation of sigma. We then essentially draw this random sample of properties of size n, so that could be 10 properties or 5 properties or 20 properties each time. And then with n being sufficiently large enough, so let's just say, okay, rather than using 10, 5, 20, let's just say we draw 50 each time. Then essentially we will basically get a distribution of sample means that we pull each time, which are normally distributed, okay? So that means that the distribution of those sample means, if we plot them each time, we take 50 premises each time that we want to sample the house price for, we'll end up with a bell-shaped curve, okay? That Gaussian, normally distributed shape for a set of data variables, and we will cover this within the actual lab that I'm going to carry out, so you can understand how this is carried out in practice. So this normal distribution has a value of mu of x bar, okay, and the standard deviation sigma of x bar. So what's the relevance? Well, most populations are not normally distributed, and that's very true because a lot of the time that I have done statistical analysis for either various projects when I was at university or later on when we've been trying to write some papers using statistical data, very often those data sets are not normally distributed, and therefore pretty much always I found that they're very skewed, and you have to kind of address this by using some kind of statistical techniques. This is important because regardless of the shape of the population distribution, the sample mean sample means as we collect them will roughly be normally distributed. Okay, so it'll be roughly normal if the sample size is large enough. So a single sample can therefore be representative of the true population because we can then take the average of all of those mean values, for example, and that should give us a fairly true representation of what the actual mean is for the whole population. So since the sample distribution is normal, we can then use the normal distribution and z-scores to measure probabilities. Okay, so you'll just need to rack your brain back. So when we covered z-scores previously, so think about what we did with probability. So the z-score, the z-score is basically a standardized measure which represents the number of standard deviations by which a value is either above or below the mean, for example. And that means we can say something about the probability of a certain outcome occurring in the future when we know where this where this kind of standardized score sits relative to the rest of the distribution, because it's going to tell us something about future probability. Okay, so we can use this information in future estimates, and that makes it very powerful. Okay, so sample mean example. So let's just say that we're picking a property at random, and this time we're going to just take one sample at a time. So essentially what we're going to do is we're going to end up with something very similar to the uniform distribution here. So let's assume that this is the underlying population distribution. We take one sample each time and estimate the mean using n1, and we end up with this quite similar looking uniform distribution. But if we actually increase the sample size, so we get n equals 5, then essentially we'll end up with this sort of bell-shaped curve, and then if we increase it to n equals 10, we start to see this normal distribution pattern occur. Okay. So we also need to think a little bit about this thing called the standard error of the mean, which basically is how the sample means actually vary. So we have this sigma x bar value, which we mentioned previously, which is basically equal to the standard deviation divided by the square root of the number of samples. Okay, and this is highly relevant because as the sample size increases, the actual error of the mean decreases in this case. And that means that we're kind of reducing the level of error that we've got in our estimation. Okay, so this is a basic measure of sample error. Okay. So in summary, look at page 118 of McGrew et al., which is basically going to give you a good overview of the central limit theorem, and read the breakout box at the bottom right-hand corner of the page. So it's basically going to summarize these principles that I state here. So if you basically approach the collection of a set of sample results, and the frequency distribution of the means will have a mean equal to the population. Okay, so we've covered that already within the kind of initial example that I gave you. The frequency distribution of the sample means will be Gaussianly distributed, so normally distributed, and the frequency distribution of the sample means will have a standard deviation which is actually equal to the standard error of the mean. Okay, so these are the principles of the central limit theorem, which then allow us to actually statistically use this to our advantage. Okay, and generally this is only applying when we use mean values as we've applied here. It kind of starts to you need a different set of principles if you're going to look at other sample statistics. It becomes slightly more nuanced, and that's why I've kind of focused on this more general mean-based approach here, because that's kind of easy for you to understand. Okay, so enough of the central limit theorem, because I appreciate that that seems quite high level and abstract to you. So let's think a little bit more now about confidence intervals, which hopefully will start to become a little bit clearer as we move through this. So this is actually providing a range within which we think the population mean, for example, would sit within, rather than as just producing maybe a single figure that we think is broadly accurate, which probably would have some sort of embedded uncertainty within it, which is obviously kind of a negative thing, because just because we think it's this value doesn't mean it necessarily is going to be. So having that confidence range provides you with a greater understanding of how much variation there might be within your data set. So, confidence intervals. An estimate of a range computed from observed data, proposing a range of plausible values for an unknown parameter. And essentially this is a proposed interval that has a level of confidence associated with it. And that confidence level, say we want to be 90% confident that the population mean falls within it, it's going to be used to our advantage, okay? Because then we can start to use that kind of probabilistic thinking that we covered within the previous lectures to actually kind of inform the likelihood of potential results being either true or false, depending on the hypothesis that we stated. Okay. So before we begin, we've got some terms that we need to learn. So you should remember now this normal distribution shape here. And we've covered this in the previous lectures, particularly in the probability part. But essentially what we're going to have is this alpha value, which is the significance level, which if you've done statistics before, then you'll probably be familiar with the idea of significance testing. But essentially this significance level refers to the probability that the interval does not include the true population mean here, okay? So it relates to the strength of the evidence before you can reject the null hypothesis. So that sounds complicated. Don't worry about it. We're going to get to it at a later stage, okay, within the next few lectures. I'm going to talk more about hypothesis testing. But let's just take, for example, a significance level of 10%. What that's going to mean is that the alpha value is 0.1 when the probability is between 0 and 1. And that means we've got a 10% chance that the mean might not fall in that confidence interval of 90% that we have. And then obviously if it's a 10% significance level, so that's the amount that there could be, so the probability for the mean not landing within that range, obviously because this is a two-tailed distribution, we have both the bottom part of the tail and the top part of the tail, that 10% needs to be divided by 2, and that provides us with 5% at the bottom end of the tail, 5% at the upper end of the tail, and then this 90% confidence interval in the middle, okay? And that's how we have our full probability distribution set up. And as I mentioned before, the confidence interval therefore is going to be 1 minus that alpha significance value, which would be 0.9 based on the idea that we had 0.1 before. And that would relate to 90% here, this portion of the distribution being covered, okay? So our 90% confidence interval spans part of the distribution, which ensures 90% of the values are actually within that part of the distribution, okay? Remember, this is all standardized based on the standard deviations around the mean, and that means we can actually use this standardized approach on any data set that we get, okay? So that's always the bit that kind of troubles me previously when I was learning this when I was your age, which is that I didn't kind of understand how this could be so widely applied to all of these different types of data sets from all of these different phenomena that we were studying. And obviously the key point is that you've got this standardization approach, okay? So common confidence levels. So this is very common to have 90% confidence, 95% confidence, or 99% confidence. And when you see statistical papers, either econometrics or other types of statistics, where they've tested a set of variables using, for example, multiple regression, as we'll cover later in this course, then actually you have these different significance levels, and often they're identified at the 90% level with maybe 1 asterisk, a 95% level with 2 asterisks, and 99% level with 3 asterisks, and they're indicating that you have these different levels of confidence that will be relevant to the analyst, okay? So you need to be aware of this. Higher confidence levels generally produce wider confidence intervals, which means that you end up with less precise estimates. But you're also reducing the sampling error if you're going to do that, because then you actually have a better chance of getting an interval within which the true population mean, for example, would sit within. And you can take a look at the table which is in the book, which is table 3.8, and this gives you an example of how you can have a significance level here which you select, so 0.2, 0.1, 0.05, etc. That relates to this confidence width as we have here. So obviously these two are complementary. They both always add up to 1 because this covers our whole probability space, the significance level and the confidence level. We then have our set number of standard errors that we get from our z-score, and then we're able to basically estimate these ranges based on the kind of the underlying absolute figures that we've got once we know the mean, for example. Okay, and then we can end up with this confidence range and a width of that confidence range. So it's worth you taking a look at this, reading the example around it, and getting into your head kind of how we set this up for different types of experiments. Okay, and thankfully we're able to do this because of the central limit theorem. Okay, so the distribution being normal, and therefore we can use z values to actually provide the probabilities that we need for defining the confidence interval. So this looks big and scary. Just bear with me here. It's actually very simple. It's basically just this equation just kind of flipped around depending on whether we're focusing on the lower bound or the upper bound. Obviously, we're focusing here on the population mean, and what we're saying is for the sample that we've got, we think that the population mean lays within, and then we set this lower bound and this upper bound, and it's going to relate to these grey parts of the distribution here. Okay, so let's focus just on this upper part first because it's easier to understand. So all this is saying here is it's the population mean, x bar, either plus or minus depending on whether you're focusing on the upper or the lower part of the distribution. You then have the z-score for the confidence level that you've got, multiplied by, and then here you put the population standard deviation, or probably you'll end up using the sample standard deviation, divided by the square root of the number of samples. Okay, and then if you focus on just the upper part of the distribution here, then obviously you're just going to have a plus sign here because you're going to have that mean value. You're then going to take the z-score that you've got, and it's going to be multiplied by that standard error of the mean. But the key part here is, remember that alpha value needs to be split in 2, divided by 2, because you're going to have 5% in the bottom part of the distribution and therefore only 5% in the upper part of the distribution. And then the only thing I would say is it's basically exactly the same equation over here on the left-hand side for the lower bound, but the difference is that you're going to be subtracting from the mean, okay? So just remember, in each case, you're starting with the mean value here, which is in the middle of the distribution. And then you're either adding an additional component to get this upper limit, or you're subtracting this additional component to get to the lower limit. And that's how you find these 2 points here within the distribution, okay? Great, so we'll cover that within later parts of the lecture today, but also in the practical. So we can define areas of significance and confidence. So before, what I was basically describing was how we get those confidence intervals. So if we're interested in a 90% confidence interval, then we're going to end up with 45% of the values falling just below the mean, 45% of the values falling just above the mean. But then we also have this additional 5% of values which fall above and below, and that's essentially where we're able to identify our kind of critical significance level in each of the tails that we're going to come back to as we start to do more kind of formalized hypothesis testing in the upcoming weeks. Okay, so just remember that this axis here is measured in the standardized units for the z, so basically for the number of standard deviations around the mean. What does that actually mean in reality? Well, imagine that we have this example here. So the image shows the true distribution at the bottom. So we have the mean here, and we have this confidence interval which stretches here, so the shaded part of the distribution. Each sample mean here has a 90% confidence interval. So this is the 90% confidence interval for this sample 1, so mean 1, mean 2, mean 3, mean 4. And then just due to randomness, each time we pull that random sample from the properties within Fairfax, that's going to essentially provide us with the ability to get a mean value. And then it's going to be different each time because we're just drawing a sample of properties. So let's just say it's 50 properties each time, and they're all going to be different properties. So we're going to end up with different means each time we pull a sample from that population. And essentially what that means at the 90% confidence level is that for every 10 samples that we actually pull from the population, only one of them is going to have a sample mean which sits outside of this confidence interval that we've actually stated. Okay, so that means that 90% of the time the sample means are always going to be within this shaded area here. So what happens if we've got fewer samples and therefore we may not be able to use the normal distribution? Okay, so let's just say that the sample size is less than 30. Let's say it's 5 or 10. Then we're going to basically have to use the t-distribution, not the normal distribution. And this gives you an example here of the differences. So if you look at the blue line, this is the normal distribution. And then if you look at the green line, basically this bottom green line here is if you use a sample of with 1 degree of freedom, and then 2, 3, 4, so on and so forth up to 30. So by the time you get into 30 samples, there's basically no difference, very little difference between the t-distribution and the normal distribution. But if you only use one sample, then you're going to have something that's probably a lot more platykurtic relative to the normal distribution. Okay, so it just means that we have to be aware of the fact that we've got fewer samples, we're going to have more error, and therefore we just need to use a different distributional shape. Okay, so it's the same as before, it's the sample mean plus or minus, but instead of a z, we've got the t value multiplied by that standard deviation value divided by the square root of the number of samples. We can also estimate intervals around proportions. Okay, so everything that we've kind of covered before, so for example, house prices in Fairfax, that would be absolute values that we've got. Okay, so if I draw 50 properties from all of the house prices, all of the properties within Fairfax, that would be an absolute value. Okay, they're the raw number within which we're actually dealing. So we're dealing with properties, and that's kind of different from proportions. Okay, whereas if we say that we're going to sample a proportion of a population, then that might be quite different. So here we represent proportion. It's not a p; it's actually the Greek letter rho, and essentially, basically, we can get this proportion value based on x over n. Okay, so x is the actual absolute value that we've got, and n is the total number of values that we have, which results in a proportion of 0.2, so 20% of the values with a specified characteristic. Okay, and basically we can then get the confidence interval for this proportion, which we can do by taking this rho value and basically adding or subtracting the z multiplied by the square root of, and then basically here for the numerator it's the rho value multiplied by 1 minus rho divided by the number of degrees of freedom. Okay, and that's how you get this confidence interval for a proportion. So let's give you an example now. So this is going to be much more concrete, and essentially we're going to go back to those kind of those raw examples, those absolute numbers that we dealt with previously, but this time I want us to think about something a little bit different. So imagine a biogeographer weighed a random sample of 30 hedgehogs. So this would be a very kind of prickly activity to do. You'd have to catch the hedgehogs, probably need to have some strong gloves on while you're doing that, and actually weigh them. So lots of time spent outside at night actually collecting these little hedgehogs. Imagine then that you actually found that the mean weight of the sample was about 0.885 kilograms and the standard deviation was 0.096 kilograms. Imagine that we then, for a 90% confidence interval for the mean, imagine that we then want to find this 90% confidence interval for the actual mean of the entire population of hedgehogs. Okay, so how do we do that? Well, we need to remember our equation. So we covered this previously, so x bar of the sample plus or minus the z-score for the confidence interval width that we want, multiplied by the standard deviation divided by the square root of the number of samples. And the way to do that, therefore, is to get the sample mean, which we know is 0.885. We then need to get the z-score, which for 90%, so we want to be 90% confidence. That means we want 90% of the values falling here, which means 45% above the mean and 45% below. So we need this, the number of standard deviations above or below the mean to represent this point, which is 1.65. And then we need to get the standard deviation. Okay, so that's been provided to us. It's 0.096. And then we have the number of samples, which was 30. So we can get the upper bound by basically saying, okay, give me the mean, and then what we want to do is we want to add on the z-score multiplied by the outcome of this standard error equation. Okay, so 0.096 divided by the square root of 30 in order to get that upper bound value, which is 0.9138. So this upper limit here is going to be 0.9138. And then we're going to do the same for the lower bound. The only difference is that here we're subtracting rather than adding, and it's going to produce this lower limit down here, which gives us our 90% sample width. Okay, so we know that if we're going to be 90% confident in our prediction that this sample mean x bar here is going to be between 0.856 and 0.914. Okay. So we're going to cover this again in R, so don't worry about it. I'm sure you'll be able to pick up the understanding for this as we start to move into the laboratory, and hopefully now you kind of start to see how we piece this together. So it looked like a really horrible equation previously, but this actually is not too hard. You just need to remember that it's a very simple equation. We just have to do it both the lower and the upper bound. So let's round off today and focus a little bit on sample size estimation. Okay, so everything that we've been doing so far is kind of estimating, given a certain number of samples and some results that we've got, where we think our population mean kind of falls between, okay, within that range, that confidence interval that we're interested in. Actually, we can use this, we can kind of flip this equation on its head in order for us to estimate how many samples we would need in order to be confident that the mean lies within a certain range. So I think this is probably going to repeat what I just said, but essentially, besides creating a confidence interval for a collected sample, we're able to calculate a priori, so before we've actually started our sampling process, before everything has begun in our empirical experiment collection process, we can calculate the sample sizes that we need to actually obtain for a certain confidence level. Okay, and this gives us certain precision within the estimates that we're going to make, which is always nice. And you should always be kind of wary when there are estimates of certain values that might be presented in a paper, for example, but they're not actually presenting any sort of confidence level or precision statistics, because then you really don't know how much kind of uncertainty is kind of embodied within those estimated values that they produce, and that's really worrying because you kind of need to understand the distribution behind those estimates in order to really understand the variability within the data. Okay, so we don't want to collect too many samples. That would be expensive both monetarily but also within our time, and we don't want to collect too few samples because that would kind of increase the error, okay, of our estimates within the parameters that we want to produce. So we want to use this approach to kind of optimize down the sample error and optimize down the burden on our time. Okay, and hopefully we can find some sort of optimal solution here. So we're optimizing time and resources in sample collection. So let's estimate the sample size. So we can rework the confidence interval equations. So instead of finding the sample size you need for a given, so instead we can find the sample size we need for kind of an exogenously defined level of error that we see fit. Okay. So the equation for the mean value in this case would be that the error would be equal to the z-score multiplied by the standard deviation over the square root of n. And therefore the key issue is that we need to arrange this so that the number of samples that we've got moves to the left, okay, because this is the part that we don't yet know. So the step firstly would be to remove the square root, which means that we can basically square all of the other items within the equation. We can then move n to the other side of the equation, and then we can move the e squared to the right to find the n value. Okay, so the n value basically ends up being equal to the z-score multiplied by the standard deviation divided by the error squared. Okay, so we're able to then find this, and we'll be able to do that for an example now, but also within the R practical. So sample sizes for estimating a mean. The equation on the prior slide needs population standard deviation, which unfortunately we probably don't have. So we basically have to substitute in the population standard deviation and actually just use the sample standard deviation. So we can either take this from previous studies, we can make an educated guess from experience or logic, or we're able to actually take a preliminary sample, which is probably the best approach, the most likely approach that we will use if we're going to go out and actually carry out a sample exercise. So if we're going to do a pretest, as I suggest here, then what we're going to need to do is basically a two-stage sampling design, and we're going to reuse some of those samples. So let's say we sample 30 in order to estimate a parameter. If 50 total samples are then needed, we would need to return to the population to collect the additional 20 in order for us to get to our ideal 50 samples. Okay, so we would pre-sample 30, get the value that we needed, and then when we've got that information, we can return and collect the final 20, knowing then that we need 50. Okay. So how do we do this in practice? Well, Suppose you want to estimate the mean yield of corn per acre to a confidence level of 95%. Okay, so we're going back to the agricultural examples that I've previously given. So I'm not a farmer, but let's just say for this instance that we are. And then essentially we want to estimate the mean yield of corn that we're going to get per acre so that we can do some business analysis, we can do some estimates for how much money we might make based on a particular crop in a particular field. So let's assume that we basically take a preliminary sample of 50 acres and we find that the mean is basically 74 bushels of corn per acre with a standard deviation of 16.65 bushels. So then how many acres do you need to actually sample in order to be within 3 bushels of the true mean? Okay, so remember that we need to get the number of samples. So we need the number of acres that we need to actually survey, and we get that by basically getting the z-score, which we know because we basically want to be confident to 95%. So we need to find this 95% value, which captures 0.475 of the value, so 47.5% of the values in the upper half and 47.5% of the values in the lower half around the mean. So we need to get that value, and then essentially we need to multiply it by the standard deviation, which we have already, thankfully, because we've already done some surveying, and we need to divide it by the error of the mean. So we've already said we want to be within 3 bushels of the true mean. Okay, so we want a fairly accurate prediction, which means we're going to need to do some math. So in order to get this n value, so how many acres we should survey, it's going to be 1.96 because that's 1.9 standard deviations above the mean for this upper limit here, and 1.96 standard deviations below the mean here. So these are, remember, these standardized z-scores that we've covered many times before. And then we need to multiply by the 16.65 bushels here in order to get the numerator, and then we can divide it by the standard error that we've accepted, which is 3, and basically then we can square them, and that gives us 118.32 acres that we would basically need to actually survey in order to be 95% confident that our true mean lies within 3 bushels. So as the actual sample, the initial sample covered 50 acres, we therefore need to kind of subtract this from this 118.32 acres that we need to cover. So if we take 118.3265 minus 50, we get 68.3265. Obviously, we don't want to sample 0.3265 acres, and therefore we round up. Okay, so we always want to round up to make sure that we're covering that full unit in the final acre that we're going to sample in this case. So basically we get 69 acres, and that's the number of which we need to go out and sample in order to make sure that we get this the level of precision that we want on this particular question. Okay, so for how many acres we need to sample to be within 3 bushels of the true mean. This is going to give us a very, very accurate estimate of the true population parameter. Okay, so thanks for tuning in today, ladies and gentlemen. We've covered some of those more advanced sampling approaches. So previously in the sampling lecture, we covered different ways in order to kind of structure the sampling. So that was in last week's lecture. This week we actually got into confidence intervals and then actually estimating how large our samples needed to be in order to provide a certain level of precision for estimating a population parameter. Obviously, this has been quite high level, and therefore what we're going to be doing in the lab today is actually going over in R some of these examples and then producing them by hand, and then hopefully all of the pieces of the jigsaw will kind of fit into place for you to kind of take this information and then work on the assignment which I'm going to set today, which will be due in a week's time, okay, on the Thursday in the following week. Great, well, thanks for tuning in. It was nice to see you all, and I'll look forward to seeing you all within the laboratory session. Goodbye.